So hi everyone, I'm Aishwarya. I'm here to present our work Ionia, which is a high-performance replication protocol for modern disk-based key-value stores. So a lot of key-value stores that are popular today are built atop write-optimized structures such as log-structured merge trees or LSMs or B-epsilon trees. Examples of these include popular key-value stores like RocksDB, LevelDB, and even replicated stores like Cassandra. And these are widely used because these stores offer a lot of performance advantages, especially with respect to writes compared to those that are built atop B+ trees. And even recent ones are designed for and optimized for modern SSDs and can even extract the high throughput that modern SSDs have to offer, and then they can do so at low latencies. So as these stores are very popular, they are often deployed in data centers. And when you do so, you have to ensure that they are being done, these stores are deployed in a fault-tolerant manner, right? A popular approach to ensuring fault tolerance for these key-value stores is to run multiple replicas of these key-value stores on multiple nodes, right? And then you layer a replication protocol like Paxos or Raft on top of this. So this replication protocol would coordinate updates and reads to the underlying local storage to ensure strong consistency. However, when you do so in existing approaches, you do so in a black box manner, in that the above layer, that is the replication protocol, is oblivious to some of the properties of the local storage engine, and we showed that this black box layering leads to poor performance. In particular, this often leads to high latencies and low throughput. So in our work, we advocate that we should break this black box layering, and we advocate for designing the replication layer to be more aware of the underlying local storage engine. So to this end, we design Ionia, a new replication protocol that is optimized and designed specifically for write-optimized key-value stores. So Ionia exploits the unique characteristics of the underlying write-optimized key-value stores and is able to achieve much better performance than traditional and optimized replication protocols. So that was a quick introduction to the talk, and I'll now present some background and then talk about the key ideas in Ionia, and then present some design aspects, and then finally present some results. So I'll present some background on write-optimized key-value stores that's important to understand Ionia, and we'll specifically talk about the characteristic that we are going to exploit in Ionia. So as I mentioned, right, write-optimized key-value stores are those that are built atop write-optimized indexes such as LSMs or B-epsilon trees. These stores exhibit what we refer to as read-write performance asymmetry. So because these stores are write-optimized, they can extract the sequential bandwidth of the underlying device on writes because they do a bunch of writes together, like they avoid random I/O, and then on writes they are able to extract the sequential bandwidth of the underlying device. But unfortunately, reads are still bottlenecked by the random IOPS of the device, right? This is similar to B+ trees. So as a result, what happens is that in these stores, writes tend to be much more performant than reads. So that's the read-write asymmetry. So an important implication of this read-write asymmetry for these stores is that these stores are designed in such a way that they avoid any queries on updates. This is important for performance. So on every update, if you end up performing a query, then essentially you would squander the benefits of write optimization, right? So as a result, these stores convert all sort of updates into blind mutations or blind writes. So writes do not return any execution results or errors. For example, if you consider the popular put in key-value stores, put returns only an acknowledgement. It does not return any execution result. Similarly, put also does not return an execution error if, let's say, the key that you're trying to insert is already present, right? Even read-modified writes that typically tend to return results do not return results in these write-optimized key-value stores. So they are often converted into some functions that are recorded in the key-value store, which are executed later. Okay, now let's talk about consistent replication for these key-value stores. So these are protocols like Paxos or Raft when used to build a consistent replicated key-value store. So typically you have many replicas that are running, and one of them is designated to be the leader, and others are called followers. Let's suppose the client wants to perform a write. The client sends the request to the leader. The leader would then append this write to a log. the leader would also ask the followers to do so. And once enough nodes have recorded the update and have agreed upon the order, the leader executes the operation on the key value store and then returns the result. So this incurs 2 round trips. And the background, the leader will also ask the followers to apply the updates to the store. So this leads to high latencies on reads. So in particular, you incur 2 round trips to perform any writes. And then to ensure consistency, all the replicas also end up applying the updates on a single thread. Because if you end up applying the same sequence of updates, but on different threads, then the threads might interleave in different orders, and then you would have, the replicas would end up diverging. So to avoid that, strongly consistent replication protocols enforce all the updates to be applied in a single thread. And that leads to very low throughput. That's writes. Now let's talk about reads. So to ensure strong consistency in these stores, reads are always redirected to the leader. That helps you in achieving low latency reads, so you can complete the reads in 1 round trip. But you're not able to scale the reads by using all the replicas, so your read throughput is just limited by the performance of the leader. And this is again required to ensure strong consistency. So this is particularly bad for write-optimized key-value stores, because if you redirect all the reads to the leader would now have more reads to serve. And as you increase the number of reads on a particular node in a write-optimized key-value store, the performance of the system goes down because of the read-write asymmetry that I talked about earlier. So of course, many prior work has tried to improve the performance of the replication protocols, specifically try to address the concerns related to low throughput and high latencies. But these are protocols that are oblivious to the underlying storage. These are general optimizations. But what we find is that all of them fall short. I'll now go over them one by one. So we're going to look at these protocols on 3 axes. First, we are going to look at the performance of these write performance of these protocols. Then we're going to look at the performance of reads. In particular, can reads scale, and do they offer low latency reads? And then we are also going to look at the availability of these systems. First, let's talk about an unreplicated baseline, right? This is a non-fault tolerant system, so you're not replicating data. This is an unreplicated baseline where you just have a standalone key value store that's running. So this is going to give you good performance for writes. And then it's also going to give you low latency reads. Of course, this is not going to scale, and then you cannot tolerate failures. And then you have Paxos or RAF, which I described in the previous slide. So this incurs high latencies for writes and reads, for writes, and then it incurs low throughput, but it can tolerate failures, right? So to overcome these problems with Paxos, people have proposed many optimizations. So you can divide them into 2 categories. One set of optimizations try to improve writes, the other set of optimizations try to improve reads. Let's first look at writes. A class of write protocols try to improve the write throughput of these systems by leveraging parallel execution. So they build safe parallel execution protocols that ensure that even though you apply operations in parallel, you can still do so in a safe manner, right? However, unfortunately, these protocols incur high latencies. On the other hand, you have a lot of protocols that try to improve the latencies of writes. So these are low latency protocols. Although they improve the performance of writes in terms of latencies, they still give up on throughput, which is very important when you want to extract the performance of the underlying storage. So that's writes. Now you have a lot of protocols that have also tried to improve the performance of reads. So we have protocols like Gaios that try to scale reads. They do so successfully, but they give up latency for that. So these protocols incur high read latencies, in addition to incurring also high write latencies. And then you have a class of protocols that can achieve both scalable reads and low latency reads, but they do so at the cost of write performance and, more importantly, write availability. I'll talk about these class of protocols in a bit more detail when I talk about Ionia. An ideal system that we want to build should match the performance of an unreplicated system for writes, and then it should be able to scale reads by using all the replicas, and then do so with low latency without compromising on availability or slowness tolerance. And now I will talk about how we can design one such protocol for write-optimized key-value stores when we make use of the properties of these stores. So that's going to be Ionia. So Ionia uses 3 key ideas to improve over existing work. The first key idea focuses on writes, and the second and the third ideas focus on providing low latency scalable reads. I'll go over them one by one. So for providing high throughput writes, Ionia borrows the idea of parallel execution from existing parallel execution protocols. So at a high level, the key idea there is enforcing all non-conflicting writes to happen in parallel, but then ensuring that whenever writes conflict, they happen in the same order across all replicas. I'm not going to go over the detail because it's mostly borrowed from existing work. But these existing high throughput protocols suffer from high latencies. What we realize is that we can avoid these high latencies by exploiting the interface semantics of these write-optimized key-value stores. That is, in particular, these write-optimized key-value stores do not return any execution result because they want to avoid query before updates, right? So based on our prior work scatters, we realized that we can defer execution and achieve low latency. And we do so while enforcing strong consistency because we make everything durable in the synchronous path of writes. But Skiros does not provide parallel execution, but we are able to combine the ideas of parallel execution and defer the parallel execution with immediate durability. And as a result, we are able to achieve both one round trip writes and high throughput, unlike prior approaches. Now let's talk about the read path. But before that, I want to give a background on some existing protocols to understand our read protocol a little bit better. So we observed that existing approaches that are there for providing scalable low latency reads conflate what we call scalability and locality. Okay? So these protocols are designed for in-memory key value stores. So in-memory key value stores where they assume that everything is going to fit in memory, network tends to be the bottleneck. So the way these protocols ensure that you can have scalable reads is that they enforce whenever you want to perform a read at a replica, the read should be local. That is, you cannot generate any additional message for the read that you're doing at a replica. Because if you do so, because the network is the bottleneck, the system would not scale. Right? So these protocols conflate scalability and locality. But this has a critical implication because you cannot send any additional messages or perform any checks by contacting other nodes. Your writes have to be performed on all the nodes in the synchronous path, right? This is to ensure strong consistency. So it's typically performed on a quorum, but here you have to ensure that writes are done in all the replicas in the system. As a result, of course, your write performance is going to become very bad, so you're going to incur high latencies. But not just that, you also cannot now tolerate failures. Even if a single node fails, your writes cannot proceed, right? So the only way to sort of get out of this is to reconfigure the system and remove that failed replica. This is unlike existing protocols that can tolerate 1 or 2 nodes failing, right? And of course, you cannot also tolerate some of the nodes being slow. So these existing low latency and scalable protocols make this fundamental trade-off where they trade off write availability and write performance to achieve low latency scalable reads. We realize that in SSD-based write-optimized key-value stores, SSD's random IOPS is the bottleneck and not the network messages. So reads can scale even if they are non-local, right? So even if you, let's say, you want to perform a read at a replica, you can send additional messages to other replicas to confirm the status of the read. But when you do so, you need to ensure that this additional messages only access the in-memory state on the other replicas and not something that resides on the SSD. So we realized that you can decouple scalability from locality in SSD-based key-value stores. So in Ionia, writes are performed only on a quorum. So this guarantees availability and slowness tolerance. And to handle stale replicas, whenever Ionia performs a read at a replica, it also issues a meta query at the leader. So this meta query basically helps you identify any stale data that you might get from followers. But a key requirement for scalability is that the meta query throughput that you get at the leader should be greater than the collective IOPS or collective random IOPS across all the SSDs in the replicas, right? So, and this is true in practice. Let's suppose you have a replicated system with 5 replicas, and then you have like a fast SSD that can give you even up to 1 million IOPS. even then, we find that like even an unoptimized meta query server that we had could give you much higher throughput than the collective bandwidth of all the collective random IOPS across all the replicas. Okay, so the meta query approach that I talked about gives you consistency and scalability, but it doesn't still give you low latency reads, right? So to this end, we introduced the idea of client-side consistency check, where the idea is simple. So the clients are going to perform the meta query and the read request in parallel. So a client is going to in parallel send the meta query to the leader and the read request to the actual replica. Both of them are going to happen in parallel. Now the problem is that when the leader receives this meta query, because it's happening in parallel with the follower read, it does not really know what the status of the follower is, right? Whether the follower is lagging behind, whether it has applied all the updates or not. So that is the problem. And the solution that we do is the leader is not going to make the determination of whether or not the follower is up to date. The leader is but going to return enough information so that the client can now make this decision. And this is the idea of client-side consistency check. So the client is going to use the information from the leader that it receives on meta queries and use it to see whether or not it can trust the follower result. I'll talk about this in a little bit. So as a result, we can achieve scalable reads in one RTT without compromising on availability, unlike existing systems. I will now present some of the key design aspects in Ionia. So I'll mostly be focusing on the scalable 1RTT read path and not the write and the leader reads path. Those are in paper because this is the most interesting part in Ionia. So as I said, you have a replicated system, you have clients of leader and followers. Let's suppose the client wants to read some data item from a follower I. So the client would send the data request to that follower. In parallel, the client will also send a meta query to the leader. So the follower would access the local storage engine and then return the result for that read. So this might incur disk I/O because you cannot fit all the data in memory, so you would have to incur disk I/O in case the data is not in the in-memory cache, for example. The leader would only access an in-memory data structure and answer this meta query. And this is very important for scalability, right? If a meta query ends up accessing something on disk, then the system is not going to be scalable. So we ensure that when the reader answers the meta query, that the structure that it consults is always in memory. I'll talk about the structure in the next slide. So then now the client compares the result that it receives from the leader and the follower and it can validate whether or not it's valid. If it's valid, it's going to complete the read there. That's it, the read completes in one RTT. Otherwise, the client ends up retrying the read. Now let's talk a little bit more about like what exactly the followers and the leader return. So the follower obviously returns the actual data that you're going to read. In addition to that, it also returns the index up to which it has applied on its local storage. This is the latest, for example, the index of the latest update in its log that it has applied, right? Now the leader on a meta query returns the last index that modified the particular key that is being read. And the leader returns this information to the client. Now at the client compares these two. So the client checks if the index up to which the follower has applied is at least greater than or equal to the index of the key or the latest update to the key that the leader returned. If so, then the follower has applied everything for this key, right? All the updates for this key. So you can trust the result for this. This result is not stale, so the reads can complete there. If not, then what it means is that it's a stale, so you have to retry the request. Now I'm going to talk about like how we ensure that the meta query only consults an in-memory data structure. So the leader, for answering the meta query, what the leader needs to know is it needs to know the latest index for all the keys that were modified, right? For example, you could do this by keeping a sequence of all the updates that happened and then constructing an index on it, for example. Right? As it is, by consulting then this index that's built on this history, you can get the latest index that modified any key, right? However, the challenge is that this is impossible to keep in memory for large data sets, right? If you want to keep an index where you have the key, every key that's in the data set, and you have the latest index that modified that key in memory, it's not going to fit, especially for large data sets. But then we need to ensure that this can fit in memory for us to guarantee scalability. So that's a challenge. So our solution is that we can periodically trim this history and maintain just a compact history of recently modified keys. And that's the idea of compact history. So periodically, the leader trims this history. So that's the history above without trimming, but periodically the leader trims the history. And now the problem is that, let's say you get a key, you get a meta query for a key, for example, K1 here. The leader cannot get the information for K1 because K1 has been trimmed, right? So what do you return now? So Ionia returns what we call the latest trimmed index or LTI. This is nothing but the last index in the log that was trimmed, right? So the intuition is this. So here the LTI is 2. So the intuition is this. If you return the LTI, it's correct because the LTI is always greater than or equal to the latest index that modified that key, right? If you return the LTI, right? Because if the key is in the your history, you're going to return the actual index. If not, you're going to return the LTI. For example, here, the actual index for K1 is 1, but you can return 2 because 2 is greater than 1, so the check will fail if the follower had not applied up to 1, right? Update up to 2. And to ensure efficiency, we only garbage collects this history if we know that all the followers have applied up to that point, right? So if all the followers have applied up to a particular point, we garbage collect that history because we know that at that time, like the queries won't fail, right? The client-side consistency check would not fail if something is being accessed. And we do that even lazily for more efficiency. So that's Ionia's design. So now I'll present some quick results. So we replicate Ionia, we replicate SprinterDB with Ionia, and we compare our Ionia against many baselines. I'll first talk about how Ionia performs for write-only workload. So here we plot the throughput against latency. So unreplicated system performs really well with high throughput and low latency, but Paxos does not achieve both. Paxos parallel execution is able to achieve high throughput, but at the cost of latency. Skeros is able to improve the latency, but not throughput. Ionic can achieve both because of deferred parallel execution. Now I'll talk about how we perform on read workloads. So to do that, we have the number of replicas on the x-axis with throughput on the y-axis. And as you can see, as you increase the number of replicas, we are able to scale the throughput. And if you look at the request at each of the nodes, so here we plot the average request at every node, the requests are evenly distributed across all the replicas, but the leader ends up serving more requests. These are just meta queries that are consulting the in-memory data structure. So despite decoupling locality and scalability, because of the cheap meta query approach, Ionia is able to scale. And then the client-side consistency check, in additionally, is able to help us achieve one round of reads. So there are more details in the paper. But with this, I'll conclude my talk. So today, when we build distributed systems, we often combine layers in a black box manner, and this leads to poor performance. And in this work, we show how you can design a more performant replication protocol by being more aware of the underlying layer. But this is just one exploration. Many such opportunities can be explored when designing distributed storage protocols. And with that, I'll conclude my talk, and I'm happy to take more questions. Any questions?